So we've introduced the concept of sources, and sources are basically the input to your stream. But that, of course, raises the question of, well, where does the data go? What is the output to the stream? And so now we're going to talk about sinks, which serve that purpose. So a sink is a stage with a single input. This is the opposite of a source, which had a single output. And so here we have our nice little box diagram again. You can see the pipe coming in with the input arrow. You can think of it again as the output of the stream. And again, going back to our plumbing analogy, in our plumbing analogy, what is a sink? Well, a sink is actually exactly what it sounds like. It's a sink. When you go to the sink and you turn on the faucet, water comes out. And so you can think of the sink as the destination for that water. Now, I mean, what you do with that water is up to you. You could put it in a glass, you could put it in a pot, you could, do whatever. Similar with a sink, you could write the data to a file or a database or a REST API, etc. So the sink isn't restricting you from choosing what to do with that data. It's just providing a way that you can get that data so that you can put it wherever it needs to go. Sinks create back pressure by controlling demand. So again, thinking about our plumbing analogy, if I'm sitting at the sink and I want to signal that I am not ready for any more water, maybe my sink is full and it's about to overflow, or maybe I've just decided I don't need water anymore, I can signal back pressure simply by adjusting the faucet. So if I turn the faucet all the way off, that will signal to the upstream of the plumbing system that I'm not ready to accept any more water. What it will do is it will actually literally create back pressure. By sealing off the water flow, it creates pressure inside the pipe that then propagates upstream until eventually no water can flow anymore. Same kind of idea. A sink in Akka Streams creates back pressure simply by sending a signal upstream. Actually, more like by not sending a signal. So it doesn't send any demand signals, in which case the upstream knows it's not ready for more, and the upstream has to shut down. Not shut down, but stop pushing data. So a sink is defined as a sink, and then we see it has two type parameters, in and materialized value again. So in is the element type that's going to come into the sink. Materialized value, again, the materialized value. So sinks send demand upstream. Sink should only send demand when it's ready to receive more data. So if it is backed up for whatever reason, then it simply stops sending the demand signal, and then that will cause the flow to stop. If a sink cannot keep up with incoming data, then demand stops and the flow ceases. Sinks respond to new data in an on-push handler. So what will happen is when new data is pushed, it will trigger the on-push handler. They can also respond to an on-upstream finish or on-upstream failure. In response to an on-push request, a sink may request new data, so it may signal demand using the pull. It may also grab any data that has already been pushed, or it can cancel the stream, causing it to terminate. And again, this logic is implemented for a variety of different sinks. So we don't typically have to worry about this unless we're implementing custom sinks. Generally, this work is already done for us. But the basic logic is data is pushed downstream, which triggers the on-push handler. If you want to request more data, you can signal that using the pull method. If you want to grab the existing data, you use the grab method. And if you want to stop, then you can use the cancel method. So we have sinks that ignore elements. This is kind of the most basic sink type. So here we have a sink.ignore, which pulls all elements in the stream and discards them without processing. So this is going to give you a sink of type any with a materialized value future of done. So that future will complete when the stream is finished. So there's a quiz here. Why is there no type parameter for ignore? So the reason that there is no type parameter for ignore is because what would the type be, or does it matter? Yes, we could say I'm only going to ignore strings, but the reality of it is we're not processing those strings, we're not looking at those strings, we're not doing anything with those strings. So they might as well be any, because we're completely ignoring whatever it happens to be. So we don't have a type parameter because we're not doing anything with the elements, therefore the element type is irrelevant. We have sinks with no materialized value. So we have here sync.forEach. This pulls elements from the stream and executes a block of code on each. So in this case, for each integer in the stream, we are going to execute the print line, and then we're just going to print the value of that integer. This for each is executed purely for its side effects. No useful value is returned. Again, we just return a future of done, which means that when the stream completes, that future will complete, but we won't get a value back from it. The only value we get back is done. We can have sinks that materialize a single element. So here we have head and last. Head so these are going to pull until it finds the first or last element in the stream and materialize it. Head obviously will grab the first element. Last will grab the last element. It will fail with a no such element exception if the stream is empty. Now it's important to note that while first will consume the first element and then stop, last has to consume every element in the stream until it finds the last one. Now this of course means that if the stream is infinite, then last will never complete. So just keep that in mind. Head option and last option, similar to head and last, except instead of an exception, you get a none if the stream is empty. We have sinks that materialize all elements. Here we have toSeek. So sync.seek of integer will pull all elements in the stream and populate a sequence. So in this case, what we get back is a future of a sequence of integers. So when the stream completes, that future will complete with a sequence of integers containing all the elements from the stream. Now, of course, again, keep in mind that if the stream never completes, then that future will never complete and we'll never get back the sequence. More importantly, we could potentially be building that sequence up in memory, in which case we'll eventually run out of memory. We have stateful sinks with a materialized value. So here we have a fold. This is very similar to the fold that we saw previously with the sources. So it takes an initial value. Here we have 0. And then in this case, it's not quite the same as the fold on a source, or the unfold rather, on a source, because rather than returning a tuple, we're actually getting a tuple. And that tuple contains basically the last value that was calculated, as well as the current element. And then what we're going to do is we're going to compute the next element, and that's what will get sent into the next iteration of this function. So our fold sum is basically computing a sum of all elements using a fold, basically starting off with a value of 0, and then at each iteration it's taking the current element and adding it to the accumulated sum so far. You can achieve the same thing as in this case using a reduce. So we also have that shown here. And the difference with a reduce is that there's no need to provide an initial value, because the initial value will be the first element in the stream. So it will take the first element in the stream and the second element in the stream and then apply the function. And then it will do the same for each additional element in the stream using the return value from the previous function. We can have sinks from actors. So here we have a system.actor of creating an actor. This is kind of a weird little actor. What it does is every time it receives an integer, it adds it to a sum. So it's computing a sum. But then it has kind of a termination message, which is print sum. And if it receives that print sum, then it's going to log whatever the sum is. And so then we can leverage that using sync.actorref, and we pass it our actor as well as an onComplete message. And what that will do is when the stream completes, it will send the actor that message. In this case, our message is print sum. So when the stream completes, it will cause this actor to print out the sum. Now, of course, we may want to also terminate the actor at that point, but we haven't done that here. Be aware that this does not provide any back pressure mechanism as is. So there's no way to know whether the actor is keeping up or not. So it will just continue to push data as fast as it can. So if the actor happens to be slow, then you could end up with a mailbox overflow. You can, however, use actorref with ACK, in which case the actor can actually send an ACK back, indicating when it's finished processing a message. And if you use that, then back pressure is provided. We can have syncs to files. So here we have fileio.toPath, and that takes a file name, or sorry, a file path. And this produces a sync of byte strings, which materializes a future of IO result. And what that will do is it will take those byte strings and it will write them to the file. Of course, you will need something upstream to convert whatever your data is into byte strings. And we can have syncs to Java streams. So streamconverters.fromOutputStream creates a sync from a Java output stream. It's going to pull byte strings from upstream and write them to the output stream. Stream converters provides additional syncs as well that will allow for additional interop with Java I/O. Okay, so we're going to go ahead and practice using some of these syncs. We're going to implement the auditor class. You can see that highlighted in red. And the auditor will basically provide a few different, two, in fact, different syncs. One that will simply log elements and the other that will count elements. So we will go ahead and implement those. So in this exercise, we'll introduce an auditor who has the job of monitoring our assembly line. This will require the creation of a few syncs. So let's go ahead and do that.